because we just finished Bessel series, and just like Fourier series, you know that after Fourier series, if you take the continuum limit, you get the Fourier transform. So there's something similar in Bessel series, and you get something a transform, but you're not calling that. People are not calling that Bessel transform. It's called Hankel transform. Right. So I was planning to derive that, but I probably won't do it today. But probably I can make a video if I have time later. You could do. So the Hankel transform actually is the form is simpler than Bessel something. Bessel series seemingly, but I can just write it down for you because it has some use in some cases, like in E&M for the cylindrical problem. So you write instead of doing the Fourier series, you're now expanding it using a full range of coordinate. So the rho is from 0 to infinity. In this case, you're writing it like you're integrating d rho from 0 to infinity. Not the dk, I should say, dk. This is a transform. So you're expressing it like a Fourier transform. Superposition of different, like wave number, you call it wave number. Wave number is also 0 to infinity. And there's an amplitude, so A, K, and then J, any order of Bessel function, but for vectorality at 0, you require to be greater than -1 K rho. And similar to the definition of the scalar product, you have an extra K here, just like an extra rho in in a scalar product. So you define you can call that A as the Hankel transform of the function, and you obviously you need to find the formula for solving the unknown A when you do the expansion, and the formula turns out to be much easier. But it's actually symmetric, so it's 0 to infinity. It's this function multiplied by the same Bessel function. Okay, so this is the Hankel transform here, and you probably will see that in E&M also. But so you can just apply it for doing calculation, and to derive that using the Bessel series is just a few lines, but it's taking the continuum limit, just like what we did for the Fourier series to Fourier transform. We start with the Bessel series from equation 14.7, 47, and 48. So there's function f rho given by sum over this j from 1 to infinity. This j is to indicate the root of the Bessel function. So coefficients of j, Bessel function j nu and alpha nu j are the roots of the Bessel function j sub nu and rho a. And this is for rho is within 0 and a, and there's a restriction d greater than -1, and the coefficient c sub nu j's are given by this equation 14.48, and that we divide that 2 over a squared. There's a function j nu plus 1 at over nu j square. And there's the integration 0 to a of this function at rho multiplied by the same vector, j sub nu over nu j rho over a, and multiplied by rho and d rho. Okay, so that's the formula for the coefficient. But then we can substitute the c sub j, this formula, to the first equation, and we write it like that. So f sub rho equals to, you can write it with the integration out. We take the integration outward, and then you have rho d rho and f rho, right? And now this, when you substitute this into here, c sub j given by this one, so you sum over this. But this one going to here, so you sum over j from 1 to infinity. And now the coefficient has this, or this coefficient, c sub j has this factor in front, so a 2 over a square, j sub nu plus 1 square, alpha nu j. And then you have this j nu. This is given by this j nu. When some of this is going into here, so j nu over nu j at arms rho over a, right? And then you have this j nu, right? When we put this here, this is c sub j, right? And then there's a rho, but when we integrate that, we probably should use another variable for the integration. So we can put rho pi, rho pi, rho pi. This is rho pi, and this is following this, so this is rho pi. Okay, and now we finally multiply by this one, j nu alpha nu sub j alpha sub nu j, and times rho over a. Okay, and so that's all this. And so this is a formula for arbitrary f. So f is given by the whole thing. So in order to recover for any f, assuming obviously some well-behaved property of f, and then obviously, in order for any arbitrary f to satisfy this summation will result in a delta function. So this is what we call the completeness condition for this Bessel function basis. So sum over j from 1 to infinity 2 over a square j sub nu plus 1 square over nu j. And you have j sub nu over sub nu j rho pi over a j sub nu over sub nu j rho over a. And that must equals to, because of this, there's a rho in here, so that's 1 over rho delta rho minus rho pi. right? And you can change it to rho prime, doesn't matter because of the delta function of with the argument rho minus rho prime. This can be rho of rho prime, but that doesn't matter. And so that is regarded as the completeness condition for this basis. Now we want to take the continuum limit. What it means is with this function instead expanding in 0 to a, within this ring, we want to go to the infinite ring. We let a goes to infinity. So that a goes to infinity. Okay, and so we did in this case it means that say we define like this or this coefficient k. We can define if the alpha k is equals to alpha nu sub j and also alpha sub nu j divided by a, right? And so this is k times rho prime, this is k times rho, right? And then obviously, any finite k, because a goes to infinity, everything will be zero, k will be zero except this alpha goes to infinity. So it means that so finite k implied alpha nu j goes to infinity. Okay, that means that you are summing, although we are summing from j from 1 to infinity, basically this actually changes to almost all of this at alpha goes to infinity. All this we're summing over a large j anyway. The small j part becomes the range of the small j part. This integration is just this summation is just becomes the range becomes zero, right? In this limit a goes to infinity, and so now we can take the asymptotic values of j sub nu, and which is I think is in the chapter in a section a little later. I guess it's 14.6 or something. So you will have a section talk about the asymptotic series, the asymptotic behavior of Bessel function. And if you look up the formula, then we only need the leading term. So we look up the formula for the leading term to say sub nu plus 1 square alpha sub nu j when alpha goes to infinity or j goes to infinity, alpha also goes to infinity, obviously. That is goes to 2 over pi alpha sub nu j, and then cosine of alpha sub nu j. That's a phase, but that is not very important for our purpose. Nu plus 3/2 over t. Okay, and actually this is for j, not the square. So the square is you need the square of this, right? Okay, so that's the asymptotic expansion for j, keeping the leading order, j sub nu or j sub nu plus 1. This will go into a because all this alpha goes to infinity, and so and this summation of sum over j becomes an integration of k, right? And then the summation, because the summation for integer j, so each time j increased by 1, this alpha changes to alpha nu j becomes alpha nu j plus 1. and in the asymptotic limit, whenever this the alpha location is just the zeros of the cosine function. Now we need to look at the behavior of the zero of this Bessel function. Say, let's draw a graph, something like here. So that, well, obviously for a large J, so along J. So if J is along the axis, if J is 0, if this is the 0 of the cosine, so this is the like I should say this is our this argument, whatever this argument is, I'll call it alpha. Alpha. Okay, and this is alpha sub nu j at here. And the cosine function becomes I mean, ignore this phase. So it's 0 here. So and then so that is this is like this is the right. This is for j sub nu, right? And then the h nu is actually shifted by pi over 2. So this is if this is 0 for j sub nu, so this function is j sub nu, right? J sub nu so j sub nu alpha. So and now for the j sub nu plus 1, you actually have subtracted by so it nu becomes a nu plus 1, so it's increased by pi over 2. So you have a shift of pi over 2. So instead of 0 will be minus pi over 2, and cosine of you shift it by like a minus. So this is if you increase by pi over 2, you get to here. So so alpha minus pi over 2 is in here. So I should actually draw it like here. So this will be delayed by pi. So that will be 0 here, and then this is j nu plus 1 because of the shift of the pi over 2, right? At this location, alpha nu sub j, right? So you see that when j sub nu is 0, j sub nu plus 1 is actually minus 1. So this is minus 1, right? And then so this is j sub nu. So this will be j sub nu j alpha sub nu j. This 0 will be alpha sub nu j plus 1, right? And this distance is the increase of alpha is obviously just pi, right? And now we can have the order estimation of this summation, this part summation of j 2 over a square j sub nu plus 1 square really alpha nu j, right? And that will be the change of alpha nu j is pi. So you can say that because j is every time is changed by 1, increase by 1, say when j increase by 1, alpha increase by pi, right? And so k is so that is equals to, or transform to, so first you evaluate everything in the asymptotic limit, so you're 2 over a squared, and then this j nu plus 1, now take the square of that, and I should say this is just the cosine part is equals to minus, this cosine part equals to -1. Oh. So or maybe this is minus 2 over pi over uj. So the square will be 2 over pi alpha uj. Right? And that is this value, and then j is there's a j, delta j is equals to 1. So you actually, this becomes the summation becomes an integration, and the integration is over dk, but dk you need to make this increase by 1, and when alpha increase by pi, then k increase by pi over a, right? And so when j increase by 1, the k increase by pi over a, so dk over pi over a is becomes 1, and so this summation becomes this integration, and now you keep the other factor over here, right? And then now you see that you this equals to, so you cancel the a, cancel one of the factor a, and the a over alpha sub nu j becomes 1 over k. So this equals to so this is this part. So the whole thing becomes transform the 2, cancel the 2, and then cancel the pi, cancel one of the a, and a over alpha sub mu j is 1 over k, or you can say it becomes k dk, right? And then the other two factors. So the integration now becomes from 0 to infinity, and the two factors j nu k rho pi, j nu k rho, and the right hand side is still 1 over rho, rho minus rho pi. Okay, so that is the continuum limit of the completeness condition. Okay, and now you see that this from this form of the integration, you know that because the argument of the Bessel function is always k times rho, or k times rho pi, and just by the form and the symmetry of the form, you can say that if we, instead of integrating over k, we can say integrating over rho, a rho, and j nu. Now you have k rho, j nu, k pi rho. That would be equals to, by symmetry, basically you're calling k as rho as a k, so this becomes 1 over k delta k minus k pi. Okay, so these two relations just by the comparison with the form of the integral. Now we can use the completeness condition to do the transform. So now what we call this instead of Bessel transform, this is called the Hankel transform. F rho is given by now is k dk. We are keeping a k extra k because like all this form has a extra k in, and integrating from 0 to infinity, and then there's a coefficient a sub k and j nu k. J nu k rho, right? And this is basically just writing that any function you write it as this integral and call this a as the Hankel transform of the f function. Okay, and now to recover the formula, how you calculate a, we use one of these this form of the integration. In this case, we use the second one. Basically, we multiply the f rho with j nu k rho and multiply by rho d rho and integrate from 0 to infinity, right? And now substitute this f. This is we assume that we can expand it like that, so we substitute this into here. So you have the 0 to infinity, and now this is because we substitute this f rho into here, right? And then there's a k here, but this is an integration k, so we change that to integrating to k pi d k pi a k pi, and then you have j nu k pi rho. So everything here is this f, and then we multiply by j nu k rho and rho d rho. Okay, and this integral, and using this integral relation, so this times that times rho d rho integrating 0 to infinity is 1 over k delta k minus k pi, right? So that is and you can call at k pi instead of k, that doesn't matter, and cancel with this k pi. So that becomes 0 to infinity dk pi a k pi delta k minus k pi is equals to a sub k. Okay, and you see that so that is the transform Hankel transform formula. So this is the expansion of f into Bessel function, and the Hankel transform a is given by the same. Basically, you can say this. We write it here. So a k is equals to pretty much exactly the same form, but changing it to integrating rho d rho, and then f rho j multiplied by the same Bessel function j sub du k rho, and then you can see that this is the transform, and this you can say this is the inverse Hankel transform. They are having the same form, and so this is how you get the formula for the Hankel transform from the Bessel series.